Hi everyone. This is a video on a couple problems from our L'Hopital rule notes. It's Thursday right now, and I'm sitting in a Whole Foods. Let's look at this problem and this next one. If you go back to L'Hopital's rule, just a quick reminder, we had a couple problems in our notes and some instructions on how to handle L'Hopital's rule. You had to have a limit of a fraction going on. You had to have an indeterminate form of infinite over infinite or 0 over 0. And when that happened, you could use L'Hopital's rule. So on this problem here, not that one, this one, currently not a fraction, but pay attention to the indeterminate form. X is going to 0, natural log of x, as x goes to 0 from the right. Here you are monkey barring, you're approaching 0 from the right, and the graph decreases without bounds. So natural log of x goes to negative infinity, and our indeterminate form right now is 0 times infinity, or 0 and infinite. This is not always 0, and you need to rework this limit to put it into a fractional form to then be able to use L'Hopital's rule. So we have two pieces. We have the x piece and we have the natural log x piece. Let's build a new fraction. Let's keep the natural log of x piece in the numerator. Let's put the 1 over x, or the x piece in the denominator, but it doesn't just go like this. It doesn't just become x. It becomes x to the negative 1 or 1 over x. Now, if you look at the indeterminate form, natural log of x still goes to negative infinity. So we have an infinite numerator, denominator. This x is going to 0. And that tells us 1 over something small goes to something big. Here with infinite over infinite, and we have a fraction. Numerator is natural log of x, denominator 1 over x. You could use L'Hopital's rule. So let's say equals, going to use the rule. So put a symbol saying you're using the rule. Then let me pause real quick. Let's see. Okay, we're back. Taking L'Hopital's rule. So we keep a fraction. Numerator derivative is 1 over x. Denominator derivative is negative 1 over x squared. Both of these, numerator and denominator, go to infinite over infinite. And if you do not simplify now, L'Hopital's rule will never end. You would just keep getting indeterminate forms. So let's simplify. We have, if we simplify now, this is the limit. X goes to 0 from the right of 1 over x. So keep the numerator, dot, switch the division to multiplication, negative x squared over 1. And once we reduce our x's, we end up with negative x. You can evaluate at 0 now, and we get 0 for our limit. Next one. The limit as x goes to infinity. What is our indeterminate form? This x squared over x plus 1 is going to infinity. The degree of the numerator is higher than the degree of the denominator. This x is also going to infinity. And infinite minus infinite is another indeterminate form. If I scroll back, you'll see this is a list of other indeterminate forms. 0 times some infinite thing, positive or minus. I'm going to push pause. Okay, back. Here are those indeterminate forms for limits. Infinite minus infinite, 1 to the infinity, 0 to the 0, infinity to the 0, and let's see, this problem we had just a second ago had a 0 times infinite form. It's not of a form where you can use L'Hopital's rule yet, but it will be once you put it into a fraction, the expression. Same thing here, infinite minus infinite. We need to work this into a fraction before we can use L'Hopital's rule. So let's put this into a fraction with a common denominator. Common denominator is x plus 1, so we'd have x squared minus x, and that second x gets an x plus 1. Let's see, that's going to be x squared minus x all over x plus 1. And the two x squareds cancel. So equals limit x goes to infinity, negative x over x plus 1. Now, a couple ways, again, you could handle this. You could handle this with algebra. Right now, the indeterminate form is infinite over infinite, or negative infinite over infinite. Again, the signs don't matter. It's just that it's an infinite limit over an infinite limit. And so either we could use algebra, like we've done before, divide out all the terms by the highest power in the denominator. We could use a degree argument and say the degree of the numerator. 1 there is the same as the degree of the denominator, which is also 1. So the limit would be the ratio of leading coefficients, negative 1 over 1. Or use L'Hopital's. And if you use L'Hopital's, limit x to infinity, your derivatives would be negative 1 over 1, so negative 1. There's your limit. Okay, on Monday, we will pick up with a couple more of these problems. We'll pick up with this one and this one here. And then we will try a handful of others before moving on to antiderivatives. Okay, you take care and enjoy the rest of your day. Actually, no, I'm back. I thought maybe we should go ahead and try this one. And then we'll revisit it on Monday along with this one and a handful of others. Let's start by, well, one, checking the indeterminate form. Natural log of x goes to infinity as x gets big. 1 over x goes to 0 as x gets big. And infinity to the 0 is on your indeterminate form list from above. So to handle this, we want to get the exponent out of the exponent, 1 over x. So let's call this some limit L. And we're going to do that because now we'll take the natural log of both sides. And when we do that, it allows us, like we've done before, to bring the 1 over x out front. So here we would have limit x to infinity, natural log x to the 1 over x. And now that 1 over x can get put here. So we have 1 over x times natural log of x. And our form on the left, natural log of x is going to infinity as x gets big. Natural log of infinity is also going to infinity as x gets big. And this piece is going to 0 as the denominator gets big. So we have 0 times infinity, still indeterminate. We have to work this into a fraction. So let's keep the left side natural log of L. The right side, let's take the limit as x goes to infinity, draw a fraction. Let's keep natural log of x in the numerator, and then let's put the x in the denominator, because it's 1 over x. It's like multiplying 1 over x times natural log of x. Natural log x stays in the numerator, and then x slides over into the denominator. Now we have infinite over infinite. We could use L'Hopital's rule. So equals L'Hopital's natural log L on the left. We're only applying L'Hopital's rule to this fraction on the right. All right, derivative denominator is 1. Derivative of natural log of x. That's a composite function. Outer function is natural log. This is the inner function. So inner over inner. Inner function is natural log of x. Derivative of inner is 1 over x. If we simplify this, let's see what happens. Natural log L on the right. Let's see. We end up with 1 over, if we do copy dot flip, the x and the natural log of x end up in the denominator together. And we know both of those were going to infinity. This piece is going to infinity, so is this piece. Infinite times infinite is not an indeterminate form. So we have a fixed number, 1 over denominator getting big. That limit goes to 0. And then keep pay attention to what we have. We have natural log of L now equals 0, and this tells us that L then is e to the 0, which is 1 when you exponentiate. So again, we've done that before when we've solved exponential equations. If we make both sides exponents with a base of e, then the e and the natural log cancel on the left side, and we're left with L e to the 0. That's 1. So 1 is our limit. All right, y'all take care. Have a good rest of your day.